I, I see participants sort of coming in, but we're plateauing. So I think it would be a great time, Immanuel, for you to start your second lecture.
Beautiful. Yeah, YouTube is running, so we're all live.
All right.
Hey, great. So good to see you all back again. And it's a pleasure to start the second lecture today. And I'll promise to be in time today. So I want to talk about a few more experiments on MBL before we switch to a few other topics today on thermalization. And one thing I wanted to start out the discussion with is the question that also David raised, are there potential instabilities in the argument of MBL? And how we could maybe check for that. And actually here I've sketched out already a scenario how you could do that. You remember that we were able to project the disorder, for example, onto our atoms. And one interesting thing you could be doing would be, for example, to inject also then regions where you have no disorder in the system. You could choose even the size of those regions. And in those regions, you would, of course, expect the system to thermalize. And now you have these thermal bubbles inside, let's say, this disordered other system. So that's obviously an interesting scenario, and experiments are going in this direction. And I'll show you two experiments in this direction, two recent experiments in this direction, one from our group, and then one very recent one from Markus Greiner group in Harvard that I would like to discuss with you and what we can learn from these. Okay, so let's start. So the first experiment I want to discuss is that we basically take two of those quantum systems. We take a disordered system where we have a, let's say, spin-up component which experiences this disordered landscape, potential landscape that I showed to you. These are interacting particles, so we expect, if there is MBL, let's say we expect MBL to occur in the system, in this 2D system. And then we have what we call a clean component, let's say a spin-down component, where we only experience just lattice potential and no disorder potential. And that's what we call the clean components. We speak of one of them as the dirty component and the other one as the clean component. And now the question, of course, is, how do these, when we couple those two, how do they interact? So we have a clean component which thermalizes, which is in contact through interactions with this disordered component, dirty component. The question, of course, is what happens to this system? Now, in the situation I want to discuss for rubidium, we do this with two spin states. And I'll show you how we can make these atoms experience, one of them the disorder potential and one of them not. We have basically all the same interaction scales. That doesn't have to be the case. It just happens to be the case in this situation. So where the, for example, interaction energy between two spin downs and two spin ups and one spin up and down are the same. Caden, did you want to say something, or you're just speaking? Okay, good. Okay. Now, when we look at the evolution of the system, we can first of all look at the evolution of the independent systems when they're not coupled. So we just make either a clean component or a dirty component, and we look at the time evolution of those, and that you can see, for example, in the picture above. And again, we start with such a charge density wave state where we have, for example, the stripe pattern, which is our non-equilibrium state. We look at the time evolution of this non-equilibrium state. And we see that again, for the disordered case, we see this remnant charge density wave appear even for long times, which we hope to be a stationary limit of the system, a genuine stationary limit. And from that, we could say that the system has evidence of being in a localized phase here. And the other situation that you have is that you basically have the clean component here. And you can see here something very different happens here very, very rapidly. The charge density wave is, of course, washed out, and you basically immediately enter into a thermal state. And now you can go to the intermediate situation where we can now couple those two. We have both of those systems present at the same time, and we can change the relative number of atoms in the clean component, in the dirty component. So basically, we control the size of the bath. It's an intrinsic bath. It's not an external bath we're coupling to. It's an intrinsic thermal bath we're coupling to, made out of the clean component, and we can adjust the size of this bath, okay, by just adjusting how many particles are in that bath. And I'll show you in a second how we actually do that. Okay, so there are basically three possibilities what can happen in this situation. So we have a thermal component, a delocalized component. We have a localized component. When we bring them in contact, they can both delocalize. That would be the instability we have in the system, just everything becomes thermal. We can, of course, also have the opposite scenario where we put delocalized system and localized system into contact via interactions, and they both now localize. So localization is induced onto the delocalized component. That will be something we're calling MBL proximity effect. That in principle is also possible. And in principle, there's also a third possibility that we start with delocalized, localized, and we end with delocalized and localized also. Yeah? Even though that's probably not likely, we just have to list it as one of the additional possibilities, what can happen to this system. All right, so first of all, let me actually show you how we actually realize this potential where one component, only one spin component sees the clean lattice, sees the disorder potential, and the other spin component does not see this disorder lattice. And that's something that we call a tune-out effect, where we basically can realize a situation where the light shift, which is basically here the potential depth that we can introduce onto the atoms as a function of the wavelength, has this very different behavior for the two spin components. So let's say this is our spin down component, and this is a spin up component, which I'll show you in a second with what I'm talking about here. And then they can show very different behavior as we apply a certain polarized light field. And you can see actually, if we go to this very, very special point here, for the spin down component, we can reach a situation that we're shining light onto the atoms, but there's no resulting potential emerging. So the light shift is zero. So there's no actual potential that this component sees. At the same point, however, if we look at what's happening to the other spin component, it has a finite light shift. So it actually will see the disorder potential. So we can realize these conditions. So let me briefly explain why this occurs in atomic physics. And just switch a second to my notes here and just show you why we can do this. And let's do this for the example case of rubidium-87, again, as our toy model. That's what we're using here. And rubidium-87 is an alkali atom, so it has one outer electron. The outer shell this is placed in is the 5s1/2 state. And then we have the first excited state here, the 5p1/2 state, and the 5p3/2 state. And these are the so-called D1 and D2 lines. You've heard of those. So this is the so-called D1 line, and this is the so-called D2 line in the system. They come from the sodium. You might remember this. If you look at the sodium light out of the sodium lamps, you see these two lines, yellow lines, and these are the D1 and D2 lines in sodium, and there are similar lines also for rubidium. And now we have a ground state here for our ground state atoms. If we look at the hyperfine structure that emerges here, we have a nuclear spin of 3/2. If we couple that to the electron spin of 1/2, we get two hyperfine state. One is the F=2 state. We draw that here. So we have the F=2 state and the F=1 state are the two lowest hyperfine states, and they are separated by 6.8 gigahertz. So this is the F=2 state, and this is the F=1 state. Now let's consider our two spin states I'm talking about. So there's the spin up state, that's this state here, the F=2 MF-2 state. So let's call this the spin up state. And then there's our spin down state. Let me just choose a different color here for the spin down here. That would be this state here, the F=1 MF-1 state. And now let's shine light onto this system, which is detuned somewhere between this D1 and D2 transition, and it's sigma minus polarized. So I'm actually adding light now to the system, which creates my optical disorder potential, but I'm choosing a wavelength or frequency for that light field that it sits somewhere between this D1 and D2 line. Okay, so now let's calculate the light shifts for the two spin states that we have. So let's write down the light shift for the two spin states. And the way we calculate that is we have to now take into account that if, for example, an atom is in this spin down state, it can have a transition through the F5p1/2 state, or can have a transition through the 5p3/2 state. So there are two possibilities for a light shift to occur. So in this case, for the blue atom, we have a Rabi frequency coupling our ground state to the excited state on the D1 transition squared divided by the detuning on the D1 transition. And then we have another possibility to excite the atom on the D2 transition from that state, and with a different detuning delta D2. And now actually what you see is that in this case is here, actually this detuning, because we're sitting right between those fine structure levels here, we're tuning right between those two levels. One of those detunings will be positive and one of those detunings will be negative. So you can see that one of these terms will be positive, one will be negative. So there is a special detuning. There is a detuning for which the light shift will vanish if we tune in between this point. So there is a special detuning. That's precisely the one I showed you on the graph before, around 787 nanometers. There's a special detuning for which the light shift for that state, for the down state, vanishes. Now for the up state, what's the polarizability there? What's the light shift there? Well, that's omega d2 squared divided by delta d2. And now I want to think about, can we actually excite on the 5p 1/2 transition with sigma minus light? So we're shining in sigma minus light, and we're asking, can we excite an atom in the f equal 2 mf minus 2 to the 5p 1/2 state? My claim is no, you cannot. Is there anybody who can tell me why you cannot excite it to the 5p 1/2 state? Why there's no possibility to excite it? Why the Rabi frequency vanishes? So you can think about that as, you know, which states would we be coupling if we shine in sigma minus light? So which MF state would we couple to? So does somebody can tell me? So
you would have to go down to like MF equals -3 or something.
Exactly. So because you have a sigma minus polarized light field, the angular momentum in the z direction has to change the MF component by -1. So you'd have to couple to MF -3. But in the 5p 1/2 state, there is no MF -3 state, because the fine structure states, can somebody tell me what the possible fine structure states are in the 5p 1/2 state? So in the 5p 1/2 state, what are the possible fine structure, hyperfine structure states?
The same as the ground state, right? 1 and 2.
Exactly, 1 and 2, because you have electron spin 1/2, you're coupling to the 3/2 nuclear spin, gives you F1 and 2. So there's no F equal 3 state, which would have the MF -3 state. So here you don't have this second term. So here you have a non-vanishing light shift for this special detuning. And that's a very general scenario you can make use of. We like to do this. Now there's one caveat when you do this. You typically want to have still a large detuning to any possible, excited state, because you don't want to scatter a lot of photons. You don't want to heat the atoms a lot. So in practice, you like to do this with atoms which have a large as possible fine structure splitting. So this works particularly well in atoms which have a very large fine structure splitting. And rubidium, you have this 15 nanometers, 780, 795 nanometers. In cesium, it's 40 nanometers, but in lithium, for example, it's tiny, so it doesn't work so well, this trick in lithium. So it's something we can actually use very nicely in the heavy alkalis where we have a large fine structure splitting. So this is the trick we use. And now we can basically realize the situation I showed you, where we go to this very special point in wavelength, where one of the components will not see the disorder potential we're shining onto them, and only the other component will see that disorder light field. Okay, so then we start out by just making, let's say, atoms in the dirty component, for example, which sees the disorder. We make a stripe pattern. This is just our initial state that we can prepare in the system, our non-equilibrium state. And now we want to basically add in those clean components. How can I do that? Well, actually, that's simple. I can just drive a Rabi oscillation using a microwave transition to the clean component state. Remember, those were the F equal 2 MF -2 state and the F equal 1 MF -1 state, 6.8 gigahertz splitting. If I turn on a microwave field, I can resonantly couple them, and you start to see Rabi oscillations between those two states. So if you can just go to a specific point in time, you can tune to any ratio between the spin up and spin down component, between the clean and dirty component. I can start out here with everything in the dirty component, and go to this case where everything here is in the clean component, or to a 50-50 mixture, or anything you basically want, right? And so that's how we can tune the ratio of clean to dirty component in the system, and that's then our initial condition that we set. Now we look at how the evolution of the dirty component evolves in the imbalance that we can again evaluate easily as a function of evolution time in the system, but now also as a function of you know, how many clean components, how big is our thermal reservoir that we can couple to. So let's go slow through this. First let's have a look at the case where the clean component is 0. So we only have dirty bosons in there in the kind of disordered potential. And you can see the imbalance again goes to the steady state value, which indicates for this 1,000 tunneling times that there's localization happening in the system. And now we increase the component, the clean component, we make the bigger and bigger this intrinsic thermalizing reservoir that we have in the system. And you can see, well, for small baths, still the dirty component seems to localize, but at a lower value. So there's some kind of relaxation here going on, some lowering of the, let's say, localized fraction. But let's say after we increase the number of particles beyond a certain number here for the clean component, when this bath becomes too large, then we see actually also the dirty component completely delocalizes. And if we plot this here, and I just, you know, look, what is the steady state imbalance as a function of number of clean atoms that I have in my system. So how large is the quantum bath that I have in my system? You can see, well, if the bath is large, in our case, above about 40 atoms for our remaining 100 atoms in the system, then it seems that we definitely destabilize the system. So we basically thermalize the whole system, but for low enough bath numbers, it seems that if the bath is small enough, there seems to be localization still possible, at least again on the time scales that we're looking at, right? Okay, so that tells us something about how the size of this bath plays into the hand of this localization effect, and we can go back to our table of what we think can happen in the system.
Can I ask something?
Yes, absolutely, please.
It seems for the higher NC cases, the data looks more noisier. Is there a reason for that?
It just goes to very low imbalances. This is a logarithmic this is a logarithmic scale here. So we're going to very low imbalances here, and the very low imbalances, of course, are very hard to measure for us. So there's just more uncertainty, so the error bar is bigger. That's just kind of an artifact of this logarithmic scale, which blows them up. But of course, there's a reason for that, and the reason is, of course, that these low imbalances are really tricky for us to measure. Yeah. Very good. Thanks for the question. Any more questions at this point? Okay, so when we go back to our table, what can happen to the system? And we can definitely say that for large baths, this thing delocalizes. The whole system delocalizes. Even the dirty component cannot localize anymore. So this thermal component around it, this intrinsic quantum bath, really relaxes also the dirty component. For small baths, we can't really say. So I have to say, I really want to put a question mark here. We cannot conclusively say. There seems to be some indication if the bath is very small that this delocalization seems to stop. But again, we have to say, of course, on the time scales that we're looking at the system up to this 1,000 tau. Okay, so there seems to be the possibility, at least, that for small baths, this survives and MBL still is robust in the system up to these evolution times. And we did not see yet, if we look at the clean component, we did not see any localization effect on the clean component. So this is something we can actually rule out from the experiment. Okay. All right, so this is pretty clear. This is less clear, the second point, and the third one we can also rule out of the system. Okay, let me show you another experiment that has very recently appeared looking at these questions that I want to discuss with you. And that's basically an experiment from Markus Greiner's group, who did a very similar experiment, slightly different setting, coming to a slightly different conclusion, but I want to present it to you just to show you that really things are not really sorted out in this context yet. And so the system Markus is studying here is a one-dimensional system, again, Bose-Hubbard model. So we're just looking at the same system I was showing you before, just in one dimension now, not in 2 dimensions. He uses Aubry-André model, so it's kind of an incommensurate lattice potential that's on top of a regular lattice, which gives rise to this disorder distribution here, but he does it in a way that this incommensurate lattice potential is only present in a right-hand power side of the system, and the left-hand side of the system does not experience this disorder, so it's basically clean. So a similar setting, so you have a clean and a dirty system in contact with each other, but now in quite a little bit different setting, whereas in the 2D scenario, they were in contact to each other over the entire system size. Here, of course, in the 1D situation, those are just contacted here at this point here, where both of them become in contact. And now you can try to ask the following question. Let's say we start with the localized system, and we now couple it to this clean system here, and we look at different sizes of this clean systems. Is there a time scale where this clean system will start to delocalize the localized system? And can we deduce something like a time scale for this to happen in the system? And how large, again, has this clean system to be for us to see an effect on the disordered system? Okay. All right, so the way how Marcus does that, so basically starts with this 1/L system that you can see here. So you have 6 clean sites and 6 disordered sites. So you have 12 sites in total in the system. You have this nice quantum gas microscope images where you can see individual atoms. So you start with a state where you have exactly 1 atom per site. So 12 atoms on 12 lattice sites. You then just go to a situation where you initiate tunneling in the system. So now you can have some dynamics together with the disorder potential in the right half of the system. That will, of course, introduce particle fluctuations in the system. And then after some evolution time, Marcus can basically read out how many particles are there on these different lattice sites in the system. Okay. So basically what in the end the readout will be, the full state readout will be just to count how many particles do you find when you make a photo of the system after this evolution time on a given lattice site. Okay, and then you can of course repeat the experiment and get the statistics on the average number of particles, the fluctuations of the particle numbers on those given lattice sites. Okay, so that's the experiment he's doing. And here's the first result I want to show you. So you start with this quenched initial state, 1 atom per lattice site that you can see here. So that's characterized here. And then you evolve it. And then you, in order to quantify what you see, you introduce the density correlations in the system. And you actually introduce this density correlation operator, this connected one where you subtract from the density correlation density operator on site I multiplied by density operator on site J. You subtract the average values of the densities on these different sites I and J that you're correlating. Now for the initial state, where you have an exact number of particles, you have exactly 1 particle on site I and 1 particle on site J. The average number of particles is always 1. There's really no density redistribution happening in the system. So this quantity is always 1. This is 1 and this is 1. And will always stay 1 in the time evolution of the system, even when we have fluctuations. But in the initial state, you know, you have exactly 1 particle per site. So you multiply 1 by 1 here. So this is also 1. You subtract 1. So basically your G2 function is 0 over the entire system in the initial state. Okay. So now when you get a time evolution into the system, and let's first start with the clean system. In the clean system, what can happen now, let me remove this here. In the clean system, what of course is going to happen that these particles are going to start hopping around. Average density is going to stay 1 in the clean region, but we're going to get particle fluctuations, meaning out of a site, initial site 1, 1, we're going to make sites where we have 0 atoms here and 2 atoms on the right-hand side. Okay, so this atom here just hops onto this other site here. So out of a site, let me just draw this, out of a configuration like this, you know, you can have this particle hop over here. So you basically then have a configuration like this, where you have 2 atoms here and 0 atoms on the left-hand side. So now if you are introducing these particle number fluctuations in this clean system, what's the G2 correlator going to look like? Well, if you look at the G2 correlation function, a configuration like this, where you have 0, for example, here and 2 here, will give you 0 in this part, right? Because you have 0 atoms on site I, 2 atoms on site J, when you have such a hopping process happening. The average density is still the same, but now you see that this thing is going to give you 0, and you're subtracting the average density. So in the clean system, we expect the G2 correlator to go negative, basically indicating that we have anti-correlations in the density fluctuations in the system. Whenever 1 particle hops, the density is increased on that side, and on the other side, neighboring side has to be decreased. So those density correlations are anti-correlated with each other. And this is, of course, why we see here this negative value appear in the system. And if we go to longer evolution times, for example, 100 tau, you can see that actually this density correlations here in the clean region here basically are completely negative. So he's plotting the axis here of your system in the X and Y direction. So you can plot the density correlations in this two-dimensional plot. So this is just a G2 function of I and J that I'm plotting here. So you have the clean part, the entire clean part here, where clean is interacting with clean. And of course, on the diagonal, you know, when you're correlating the density with itself, you always have to get a positive value. So that's basically the autocorrelation part. That part will always be positive. That's not so interesting for us. Look at this part over here. This part is where you're correlating sites I with site J in the clean region, and the blue indicates that it's always negative here if you look at the scale of the G2 correlation function, these anti-correlations. Now in the localized phase, just let's have a look at what happens to the right-hand side of the system. In the MBL part where we have disorder, you see there's much less spreading going on here in this localized phase. So there is really just a little bit of spreading happening. So you just hop a little bit in your densities within the localization length of your localized orbitals. And beyond that, there's really no delocalization of the system. So here you can see that that part actually behaves completely different. But what you can also see is that if you look at especially this region where those two are in contact, this is the place where those two regions come into contact with each other, you see that in that region, in the proximity where those are in contact, you see a little bit more blue here than if you go away from that region. Okay, so this thing becomes a little bit more blue to the sides here in the proximity of the contact than if we go far away into the dirty region where we don't see as much blue here, as much anti-correlations as we see over here. And this can be quantified by summing up this G2 correlation function over all the sides of the clean system, I, and then letting this index J run over the remaining sites. Yeah? And this remaining sites can now be in either the clean part of the system, and this is what's shown here. So this is this summed up correlation function where we sum up overall the clean sites only and let one index be free, one of those density correlation indices. And we see that we get in the clean part, we get this negative anti-bunching correlations. And now we see that there's a little bit of extension of these anti-correlations going into the side of the dirty component. And this decay length that we can see here allows us to extract a decay length or a length scale over which the correlations are leaking into this dirty component. Okay, so we can extract a length scale and see how this length scale evolves as a function of time or size of the, for example, clean system. And this is what they did here and what you show in this plot here. So they measure this decay length, you know, how much do these fluctuations leak into the dirty component of the system? So how much are we starting to thermalize the dirty component of the system through this contact with the clean component? So this is the decay length as a function of evolution time in the system. And you can see that as time goes on, you more and more leak from the clean component into this dirty component of the system. And you more and more also start to introduce those density fluctuations in the dirty component, indicating that you're starting to see also thermalization in the dirty component. And okay, then, well, this may be a little bit suggestive, but there seems to be some, at least theory also suggests there's some acceleration of how this decay length grows as a function of time, which would be consistent with what you expect with this avalanche scenario that David, for example, has introduced to you in a similar setting. You can also check here how this decay length depends on system size. So let's say we change the size of the bath here, this clean bath that we're coupling to the dirty component over here. And you can actually see now as we change the size of the bath, as we make it bigger and bigger, then this decay length also seems to increase. So bigger baths seem to delocalize the localized component also in a stronger way, which is of course also something that we expect, that we saw also in the first experiment that I talked about. Finally, we can just look at, you know, what are the particle number fluctuations which should be indicative of whether we're thermalized or whether we are in this localized phase of the system, and how, you know, do distant parts of the system react in time as they're coupled to the clean component. So we're looking at the following here. We're just looking at individual sites of the chain. We're measuring the number of particles, including their fluctuations we see there in each shot of the experiment. So think about it in the following way. We do the experiments many, many times, the same experiment. Each time you will see, for example, a different number of atoms here, 0, 1, or 2. You just repeat that experiment thousands of times. You get a statistics of the particle number that you see on that site, and that's what you plot here. So this is the probability of finding 0 atoms, 1 atom, 2 atom, 3 atoms, 4 atoms, so forth at this site in the system. And we can do the same thing over here at the other end of the chain, where we have the dirty component, where we expect these localized orbitals. And if we're localized, we don't expect these density fluctuations to become so large. So we expect this original density of 1 to be more prevalent. And this is indeed what you also see. So the occupation of this site over here is close to 1, close to our initial state that we had in the system, where you don't have this thermalizing evolution. But we can ask, of course, if we're saying, if the suggestion is that this thing is thermalizing the entire system, then of course also the fluctuations over here should react at some point in time to this thermal bath that kind of creeps into the system, that also thermalizes the system, but just at a later time as a function of distance of this site from our contact point. And this is what's shown here. So you basically do this for 3 different distances from your kind of clean bath. So here this site 1, site 2, and site 3. The site 1 is closest to the clean component. The site 2 is further away, and the site 3 is farthest away from the clean component that you have in the system. And then you look at the particle number fluctuations and you calculate the entropy of that site. So what you just calculate is your log of Pn, basically sum of Pn log Pn. So if the Pn is the probability of finding 0, 1, or 2 particles in the system, you calculate this. This gives you this local entropy of this site I that you can calculate, and you basically is a measure for these fluctuations, for these particle fluctuations that you get in the system. Now, what you see nicely here for a, let's say, fixed evolution time, for short evolution times, the site closest to the clean component is already affected. And it takes longer evolution times for the site that is furthest away to become affected to also show that particle number fluctuation. So first, you see it basically is constant here, this site furthest away, and it takes some time until actually its density fluctuations also increase as a function of time. And this is what they show in this last plot here, where they plot basically how this time scale for being affected from the interface changes. And you see that actually changes exponentially with the distance from the interface. So this is our site that is furthest away from the interface, this site 6 here. And you can see it takes about 100 hopping times until that site is affected, whereas actually the site that's very close to this interface actually is already affected after very few tunneling times, hopping times in the system. Okay. So this is some evidence that indeed there is this instability going on, that when you bring this clean component in contact with the localized component, there seems to be some instability in the system, and there seems to be some avalanches, at least a scenario here where the experiment is consistent with this avalanche scenario that is predicted by theory. Okay, that's what I wanted to say about the stability. In the last part of what I want to say about MBL today, I want to also show you how we can actually dynamically probe entanglement features that are present in MBL. And the key thing I want to explain again that I talked about in the last class already was this log T entanglement entropy growth that is a hallmark feature of this MBL phase. So if you look at the MBL, at the entanglement entropy that's plotted here in numerics, so 2 papers from the Posen group and from Joel Moore's group, you can actually see that this entanglement entropy grows with this log T growth. And we saw that the reason for this log T growth was basically these Lioms, this exponentially decaying interaction strength of our local integrals of motion, which directly gave rise to this logarithmic growth of entanglement entropy. So where you split the system in 2 subsystems, left and right, you calculate for the reduced density matrix, the von Neumann entropy in the system. And the reason why this grows with log t is basically because we have this local integrals of motion, which have this exponentially decaying interactions. So we have this Liom1 and Liom2 in the system, and their interaction strength J12 was something like e to the minus x12 divided by some localization length here, xi. And that directly gave rise to this dynamical feature. So the question is, how can we actually probe that, that there is some entanglement growth happening, some interaction between distant parts of the system? And for that, I want to show you a nice protocol that was actually introduced in this paper in 2014 by Maxim Serbin and Michael Knapp and Eugene Demler, and I think Dima Abanin was also in the paper. And the idea behind this is to use a so-called DEAR protocol from NMR. And I want to explain, walk you through what's exactly happening here and why this allows us to check whether distant parts of the system are actually interacting with each other. So imagine we have this spin chain that we're talking about, and this could be now an MBL chain or not MBL chain, and we want to probe whether a system here, a spin here, actually feels the presence of some spins over here through interaction with these systems, okay? So what can we do to probe whether this spin over here actually feels interaction with this region over here? So let me show you the protocol, what's happening in this, what you can do in this spin chain. So imagine we have our spin over here that we want to measure. That's our probe. That's our system that we use to probe how much it's interacting with the other parts of the system. And for simplicity, again, we just break this down in a 2-L-bit model again in the MBL phase, where we think of this thing as one of the L-bits and the other part over here as another L-bit, but that just to simplify notation here, and it works kind of for other scenarios as well. The argument is quite general. So we start with the L-bit 1 in this spin up state here, and the L-bit 2 in this distant region in some superposition state of ups and downs. Okay, this I just wrote down one of them. It could be some arbitrary superposition state. Now, the first thing we do in this protocol is we make a pi/2 pulse on the first qubit here, which brings it also into a superposition state. Okay. Then we let the system evolve for a time t/2 with the Hamiltonian, with the interaction Hamiltonian that's present. And let's imagine this is the MBL Hamiltonian. So it's our MBL, effective MBL scenario where we have these L-bits interacting with each other. So we have this up, down, down, and up, down, and down, up spins interact with an interaction strength given by this coupling strength J12. This was this exponentially decaying coupling strength that you can see here. And we just have to evolve those states with the positive frequency value plus J12. And here, of course, when the spins are up, down, we have this negative interaction energy J12 that we have here. So we just evolve the system for a time t/2, and that's the final state of this 2-qubit system that we get after this evolution time t/2. Then we make a pi pulse on the first qubit. So we just reverse the spin, we flip the spin of the first qubit. So now what happens on that means every spin up will turn into a spin down of the first qubit, and every spin up and vice versa. Every spin down will turn into a spin up. So this first qubit here will flip into down. This qubit will flip into up. This one will flip into down, and this one will flip into up. Okay, so we just flipped the first qubit, the one, our probe qubit. We flipped the spin of that with a pi pulse. And now we let the system evolve again for another time t/2 under the same interaction Hamiltonian. Okay, let's imagine the system is localized, MBL localized, so the Hamiltonian remains the same. So now we evolve it for the same amount of time, but now you see the forward evolution that we had here is canceled by a backward evolution of the system in precisely the reverse way. And what we end up with after this evolution again of t/2 is just the initial state again. Okay, it's just the initial state as if we would not have had any interaction in the system. Okay, so if we apply another pi/2 pulse to the system, we exit with our first qubit in the spin down state. So basically by introducing this echo pulse, so this you can now look at in the sequence that we have up here. In this spin echo sequence, this is what we've been doing so far. On the spin 1, we just apply a pi/2 pulse, evolution time, pi pulse, evolution time, pi/2 pulse. And what we end up with is the spin of the first qubit in the down state. And if we would measure the coherence or the purity of that spin, we end up with a pure state of that first qubit again. We start with a pure state, we end with a pure state, okay? Now, that would not be the case if, for example, for this argument to hold, we need to have, of course, the Hamiltonian through which the system evolves to be the same at this point in time and this point in time. If anything changes in the system, the echoing will not work anymore. And that, of course, means that, for example, if these particles just move around during that time, if there's some motion here, there's some reconfiguration, then, of course, this echoing will not work anymore. So localization is key for this to work. Now, what can we do if we are localized to show that there are still interactions within the system going on? Okay, that there's still interaction of this region over here with this region over here. Well, to show that, what we can do is the following. We can actually reconfigure ourselves the spins over here in this distant region. And the way we can reconfigure those spins over here is just by applying, for example, another pi/2 pulse, but now on this distant region 2 to the system. So we just apply a pi/2 pulse over here, basically scrambling the spins, reconfiguring the spins in that region. That will lead to a different evolution of the subsequent evolution after the spin echo. And therefore, of course, the echo will not be perfect anymore, and I will not exit out of that sequence in a pure state again. And that's what you see here, actually. So if we look at how this signal would look like, this echo signal with this pi/2 pulse present or not present. If it's present, we call this the so-called DER sequence, this double electron-electron resonance sequence. So we just add this additional pi/2 pulse here on the part 2. So let's just go through the case where we don't do that. And we basically have the MBL scenario. Then we see that with spin echo, I would basically just echo out the MBL evolution, and I would end up with a nice pure state. So if I plot here purity, if this would be the purity of my first spin after this time evolution, this purity would be large, indicating that I really was able to cancel out this interaction evolution with this remainder of the system. Now, if you now re-scramble those spins over here, you're not going to be able to cancel that out, which means now after the sequence, you do expect a decaying signal of the purity of your spin. So actually in this case, the DER signal would go down because you have interactions in the system and because you scrambled the system. And that's actually different from the non-interacting system. If you would do this with the non-interacting system, if you just have a spin over here and you have spins over here, but both of them do not interact with each other, it doesn't matter whether you just scramble the spins over here, they are not affecting the coherence of the spin over here because they're simply not interacting. So in the non-interacting case, you actually, even in the DER sequence or the echo sequence, you would see a large signal of the purity of the system. And the proof that you have actually an entangling dynamics interaction in the system comes from the fact that the DER protocol now shows this decaying purity, decaying coherence on this first qubit in the system. And of course, the final thing we can discuss is, well, if you have a diffusive dynamics, if the things are moving, if everything's moving in the system, then nothing's going to help you, both for the spin echo and both for the DER sequence. You're going to get a decreasing purity for your qubit 1 state. Okay, this experiment has been done in the Google group in the superconducting qubit system. So I want to show you their experimental results on that. So you see we're discussing quite a variety of platforms. So they, again, in superconducting systems, we don't need to really understand precisely the underlying physics. Again, what the system maps to is Bose-Hubbard model. So it's the same Bose-Hubbard model that we talked about in the cold atom setting. Now we just have it in the setting of superconducting systems. We have an on-site disorder term, we have an interaction term, and we have a hopping term in the system, precisely as we would have had in the cold atom setting. So it's exactly the same model. And now we want to probe whether there's actually entangling dynamics going on within the system. So the first measurement they did was something very simple to the measurements I showed you before in the cold atom system. So they have this 1D chain, this ordered 1D chain. And they now look at, for example, how is the population on a certain qubit state, let's say qubit 9, affected over time in this setting, yeah, as we increase, for example, the disorder strength in the system. So it's like an imbalance measurement, just now focused on one site, where you measure the population of one site. And you can actually see as you increase the disorder in the system, so this is the disorder here, this W over J. So W over J characterizes disorder strength. So as you increase the disorder strength, you see that this imbalance or this population of this 9th qubit rises and does not decay anymore. And only for very long evolution times, you actually do see a decay of the system because of these technical imperfections, because of the coupling to the outside world. That would be pretty much the same interpretation that we have been doing for the cold atom experiments. Evolution times up here, we can also compare. They're about 300 hopping times, a few hundred hopping times until you get to this point. So not bad at all. So that's actually quite comparable to what we had in the cold atom case. And if we now go to this point here, where we expect the external decay not to kick in, and we plot the average population as a function of disorder strength, and we can compare it to when we deviate from a thermal expectation value, for example, here, we can basically identify the point of the transition. So we say at a point where the steady state population of that 9th qubit state deviates from the thermal expectation value that we would have for a thermal system, we must be in a localized phase. We can say, okay, then this happens around this value that you can see here of the disorder strength over kinetic energy of about, again, 3 to 4. Again, pretty similar to what you have been seeing in the cold atom experiments. Now, that's the same thing I showed you before, but now I wanted to actually show you the DEAR protocol. So they did exactly the protocol I showed you before. So they basically take one qubit as the reference qubit, where they want to measure the purity of that qubit. And they do the pi/2 pi/2 pulse sequence that you can see here. So this is basically what's done to your qubit that you're measuring, this red sequence, pi/2, pi pulse, echo pulse, and then another pi/2 pulse, or you don't need that and you just measure. This is our Ramsey sequence that we're basically applying to that sensing qubit. Then we have interlace in between that, we can lace the many-body evolution of our other parts of the system. And then we can add to a distant part of the system, to a distant qubit, we can add this DEAR pi/2 pulse, which scrambles the spin in a distant region. And we can try to see, is there an effect now on the coherence of my system? Okay, so what they plot is the state purity of the sensing qubit. So this is the purity here of this qubit, that is our sensing qubit, as a function of evolution time in the system. And ideally, it should just, stay very high. And you see, well, it decays a little bit. But then if you just have that the spin echo protocol, which is this red line here, it goes to this steady state value here. And now you basically start to couple in, you start to scramble distant regions of the system. So now you add that DEAR pulse to distant parts of the system, and they are marked here. They've marked here where they've added the DEAR pulse. So first of all, they add a DEAR pulse to this qubit, which is now 5 sites away. And you see, well, okay, a little bit, this decays a bit more. Now we can go closer. And we can now scramble a qubit, which is much more in the vicinity of our sensing qubit. And there you can see, actually, well, in this case, actually it decays much, much stronger. Okay. And that, of course, means we had a stronger interaction between the local integrals of motion between the sensing qubit and the one that we're probing, where we're scrambling the spins, very much in agreement what we would have expected in the system. And from this signal strength, you can actually deduce something about the interaction energy between those qubits. So again, the idea is, to recap, is to have a probe qubit somewhere in a region in space, have a many-body time evolution of the entire system that you can echo out, and you kill the echo out possibility by scrambling some distant spins. And if there's an interaction between your sensing qubit and these distant spins, they will sense that these spins have been scrambled. The echoing will not be perfect anymore, and you will see that as a decreasing purity of your signal. And that's precisely what you see in this experiment here in the superconducting chip. Okay. So that's how this DEAR protocol works, how you can use that actually to probe whether two parts of your system do interact with each other as a function of time. It's a quite general technique you can especially usefully apply to these localized systems, but you can apply it basically in very general scenarios. Okay, so that's all I wanted to say about MBL. So I hope we touched upon a few important points on MBL. I think there are, of course, big open questions, as also David, I think, showed to you in general on the whole stability question. Some of them we might be able to answer experiments, others might be really not be able to answer. I think even with factors of 10 or 100 improvement in the experiment, we might not be able to improve that. There's a lot to be said, which I didn't talk about, on the nature of the transport in this ergodic, in this thermalizing phase when you get close to the MBL phase. There's the question of this finite couplings to the bath, which I think we have some first experiments which show us some behavior, but I think we need much more to understand better the timescales that emerge in 1D and 2D that give rise to these instabilities, to really judge whether these instabilities are relevant on any experimental timescales for large system sizes. And the general challenge for any experiment to answer these questions is you need to push your systems to long evolution times. It's the physics of long evolution times that we're looking at here. We need to look at large system sizes, and combining both really pushes us with what we're able to do in the lab. So really have to challenge our quantum simulators, quantum computers, whatever you use to probe this physics, to go to long time scales, long coherent isolated evolutions, and large system sizes. Okay, that's all I wanted to say about MBL, but I want to switch to a topic that's related, and that's the question of thermalization. And since we saw now systems that do not thermalize, how we can probe that, the question is, of course, how we can probe thermalization in the system. And there I want to discuss another very nice experiment from Marcus' group from 2016, I think, on the quantum thermalization of this isolated system. And it brings me back to the initial setting I discussed with you in the context of MBL, that we're thinking about a isolated quantum system, which is in a pure state. And we undergo, for example, a certain quench dynamics, which means we suddenly change the Hamiltonian parameters. So let's say we start in an eigenstate of the system here, in a pure state, which is an eigenstate of our Hamiltonian H1. And then we change rapidly our Hamiltonian to H2. So the initial state is not an eigenstate anymore of H2. So of course we expect a strong dynamical evolution now of the system. The initial state is still a pure state. And you know, of course, that we just have an isolated system. We evolve with the Hamiltonian H2 now, this pure state, it will stay a pure state. So it's still a pure state, but something has changed. And of course, what has changed in the system, that we had a lot of entanglement that has been distributed in the system because we had a lot of motion, a lot of dynamical evolution in the system. And this entangling evolution, which is kind of sketched out here in this picture, where you now have like distant particles becoming entangled with each other, this gives rise to a thermalization behavior on local scales of the system, so that the system locally looks like a thermal system. What do we mean by that, that it looks locally like a thermal system? Well, again, if I take a box here, a small box, then basically the state of that system, the density matrix of that local box, should be described by a thermal density matrix, as you can see here. So that's our thermal density matrix, diagonal density matrix. We can ascribe a temperature to that system that we see, right? Now, it turns out what I will show you, what's interesting here is actually this assumption that this thermal density matrix appears. That's equivalent to saying that the von Neumann entropy of this subsystem A is equal to our thermal entropy. So remember how thermal entropy is defined. So if we have a thermal system with a thermal density matrix, then we would just define the thermal entropy through this formula here, where this rho A is our thermal density matrix. But if we have a pure system, I can also calculate a reduced density matrix of the system. I can just calculate the rho A also through a reduced density matrix of the system. And then the von Neumann entropy would be given by the same formula, but now the rho A here is actually the reduced density matrix of my system, where I trace out a remaining part B of my system, reduced density matrix, where we basically take this pure state and we trace out this part of the system, this remaining part of the system here, B. We get a reduced density matrix. We can calculate the von Neumann entropy. And the fact that we expect this to be a thermal density matrix means that this von Neumann entropy is equal to the thermal density matrix in the system. So basically, the thermal entropy that we have corresponds to the von Neumann entropy that we can calculate through the reduced density matrix. So in a way, this outer part of the system acts as a thermal reservoir through the smaller system, and through the entangling dynamics that we have in the system, we basically have this thermal behavior appear in the system, and that's something we would like to actually check in the experiment. Now, there are two things that are really important that we need to check. What do we need? What are three things actually that we need to show this evolution? First of all, we have to show that we're dealing with an isolated system, or we're just having Hamiltonian quantum evolution. If we have an isolated system, which is initially in a pure state, then if we evolve with a Hamiltonian, the system, the global state of the system remains pure. So I have to prove to you that the global state, even after this quench dynamics, is a pure state. Locally, it's thermal. It looks like a thermal state. It's not pure. But the global state should remain pure if we have just purely Hamiltonian evolution and not coupling to some, let's say, outside bath, which is not what we want to show here. We want to show that the system itself basically has this thermalizing evolution in the local scale, and on a global scale remains pure. And then, of course, we need to probe locally this von Neumann entanglement entropy or a related quantity in the experiment. And here's a trick. So how do we measure purity? Well, what's purity? How is it defined? Well, the purity of a quantum system is defined by the trace of the rho squared of the density matrix squared in the system. That tells us something about the purity. And a related quantity to that is the so-called Rene-2 entropy, which is basically the negative logarithm of the purity, which gives us an entropy. And it turns out that this, actually let me turn this away, that this is something you can measure. So it's really hard to measure von Neumann entropy, but this Rene entropy, which again is related to the purity of your state, which tells us something about the purity of the state or how mixed our state is, this is something we can actually measure, and I'll show you in a second how. It also actually is a bound to the von Neumann entropy. So von Neumann entropy is bounded, you can show by this Rene-2 entropy. So von Neumann entropy will always be larger than this quantity that we can measure in the system, okay? So how can you measure this Rene-2 entropy in your system? And this is a very nice proposal from Dieter Jaksch and Peter Zoller's group, who devised this protocol. And I will not be able to explain in detail how it works, but I really urge you to read the papers and find out for yourself how it works. It's basically like a big quantum many-body Hong-U-Mandel experiment that you might remember from your quantum optics course for single photons on a beam splitter. This is basically doing the same thing for a many-body system. So the idea is you take two identical copies of your system. So you prepare the system in two exactly identical copies. You evolve them through the same Hamiltonian. So again, you have two identical copies evolved through the same Hamiltonian. And then you basically have to have a beam splitter operation between the sites of those identical systems. Let's imagine these are 1D systems. And we now basically have to have a beam splitter operation here. If you think of these as two sites, you can think of this as now basically a double well, where you can just lower this potential and have them oscillate for a quarter of an oscillation period. So we basically realize a beam splitter operation between those two sites. And then we just have to make a parity measurement of the occupations of those different sites after interfering those many-body copies after this time evolution. And this parity measurement will then, as you can show, directly give me the purity of the quantum state. So let me show you how this works actually in the case of what Markus did in the experiment. Let's go through the sequence protocol first, and then let's look at the measurements, how this is done. So you have to create two copies, identical copies first. So what he did here, he created two copies out of this one-dimensional systems. So you have two 1D systems, 6 sites, exactly 1 atom per lattice site initially. That's something we can prepare very well in the lab through this mod insulator state. So you have two copies, exactly 1 atom per site, two 1D systems. These are our two copies. Then we let them evolve in the 1D system only. So we let each of those 1D system evolve with the same Hamiltonian, okay? And then we do this many-body beam splitter where we now interfere those two many-body states with a beam splitter operation, and then we measure the parity of the resulting state. I'll show you how to do that in a second. And from this parity measurement, you can retrieve the purity of the states that you had in the individual 1D systems. You can say how pure was this state that evolved over this time. Okay, so here's actually the result that you can see. So here's the measurement of the purity through this many-body interference experiment, where you measure this trace of the rho squared as a function of evolution time, quench time in this many-body system, where you start out with a very deep lattice, atoms pinned, you jump to a shallow lattice, atoms can move very easily, and you can actually see, well, in a perfect world, this purity would be 1, would be up here, the purity would be 1. Okay, you start out, you see even at time t equals 0, it's not exactly 1 because you have some experimental imperfections, but it's kind of high, close to 1. And during the evolution of the system, it stays at the same value. The purity stays the same during the Hamiltonian evolution from here to here. Okay, so as the system evolves from here to here, the system remains in a pure state globally. But locally, if we look at locally at the system, we can measure, for example, the particle number fluctuations locally on a given lattice site. We start out with this state here where we have exactly 1 atom per lattice site in the initial state. And after this evolution time, if we would measure the number of particles on that same lattice site, we would see actually that's now has this interesting distribution function. And if you compare what a thermal state would look like, actually this exactly matches the populations of how a thermal state would look like locally. So this is our local observable, is the atom number, counting the atom numbers on the local site. That's the observable we're looking at. And we see that the observable here has a mean and fluctuations, a whole distribution function, which exactly matches the one that you expect from a thermal state in the system. Okay, so here's how this works in practice, how you measure this purity, just to show the protocol. So this purity—
Can I ask a question real quick?
Yes.
So I was curious about this beam splitter operation that you mentioned.
Yes.
What exactly does that mean in terms of the, say, like the Fock basis for that side?
Basically, it just takes a destruction operator on this lattice site into a superposition of symmetric and anti-symmetric destruction operators between the two sites, neighboring sites. So it's like one mode coupled to two modes. Right, that's like our beam splitter operation. And here what we're actually doing in practice, you're basically doing this double well. This would be the single side. This would be one side of the system. This would be another side of the system. You lower the potential well here. You couple them. You let them evolve through quarter oscillation periods. So they can tunnel now through quarter of a period. And then you raise the barrier again to turn off the beam splitter again, and that has completed exactly your beam splitter operation. Okay, so in terms of the Fock state operators for creating or destroying a particle on that site, it brings that single Fock state operator into a superposition of the two Fock state operators, creation and destruction operators for those two modes. And the beam splitter actually now acts, this is important, does not act along the chain, but across the chain. You're really interfering those independent copies now. Remember, these were the independent copies. They were evolving for a certain amount of time. And this is then what you might get. You might find 0 atoms here, 1 atom here, 2 atom here, 2 atom here, 0, 1. This could be a result from a single measurement in your system. And this would be the result down here. It gives another kind of random result. Actually, how you measure that is shown here. So how do you measure 0, 1, or 2, or 3 atoms on a given lattice site? You basically just let the atoms tunnel in the transverse direction. So you let them move away in the transverse direction. And this is shown here. So you started in this original line here. You let the atoms move away, and then you just count the number of atoms on these specific lattice sites. I don't know if Wasim discussed with you this parity projection effect in quantum gas microscopy. This is how you avoid that, how you can fully count all kind of atom numbers that are present on a given lattice site. Okay, but that's just a side remark. So what you do now, you have the same time evolution that we have here, and now you have this beam splitter operation here, and then you do the counting. That's now the thing you do. Okay, so then you count. And then you say you find 1 atom here, 3 atoms here, 1 atom here, 0 atoms here, 1 atom here, 2 atom here. That's, for example, something you will find in the upper chain after the beam splitter, and the lower chain will look like this. And now how can we retrieve the purity? The purity you can show, and that's these papers I showed you, is just a product of the parities of the occupation numbers of those different lattice sites. So let's walk through this. So you measure 1 atom here. That's an odd number of particles. That would give us a parity of -1. You measure 3 atoms on the next site. That's again an odd number. That's again a -1 parity. So you mark down a -1 parity for that site. This site has 1 atom, again, a -1 parity. This site has 0 atoms. That's an even number of atoms. So you mark down a +1 parity for that state, -1 for this state, +1 for that state. Okay. Then you multiply those numbers. -1, -1, -1, 1 gives us a -1 multiplied by -1 gives us a +1 multiplied by 1, a +1 gives us a total parity of the system of +1. And that's the quantity that you can show this product of these parities after the beam splitter measurement. This is precisely, it turns out, for the bosons that we're looking at here, this Renyi 2 entropy that you want to measure. So this is how this is done in practice, actually, in the experiment. Okay. All right. So now you can do this and this is how this graph was then created. So you can measure this now for different evolution times. You can measure the Renyi 2 entropy or the purity of the system, and you can see actually that the system remains pure over the entire evolution times. Now you can also not do this for the entire system, but you can select subsystems and measure the Renyi 2 entropy, remember, which is a proxy for the von Neumann entropy in the system, the entanglement entropy. You can measure that for different system sizes. So let's start here with this point again. This is the entire system. That's what we know. That's what we looked at already. The purity was 1, meaning the entropy, the Renyi entropy, which is the logarithm of this quantity, is going to be 0, close to 0, right? And okay, it's not perfectly 0. It has some finite value, but it's basically close to 0, showing that we have this high purity state. For the entire system, we're remaining in a pure state. But now we can pick different local systems and do precisely the same measurement. We can pick a local system which is just consisting of 1 side. We can pick a local system which is consistent of 2 sides. We can pick a local system which is consistent of 3 sides in the system and do the same measurement protocol, but just for this 1, 2, or 3 side systems, and measure the purity of those subsystems now that we have in the system, okay? And for these subsystems, you can actually see, well, actually for those subsystems, we see this Renyi entropy grow, this entanglement entropy grow, and then saturate to a specific level. And the value it grows to depends, of course, on the subsystem size we're looking at. And the time scale over which this actually saturates here to its final value actually also depends on the propagation speed of information in the system. Now, what's nice is that you can actually show that these values actually agree with the thermal entropy values that you would expect for thermal states. If you would assume a thermal state in the system, you can show that these Renyi 2 entropy values agree with those values, showing you indeed that the entanglement entropy that you measure corresponds to the thermal entropy in the system. So here, finally, I want to summarize what this experiment is doing and how it's showing the thermalization of the system and how we can compare that to different thermal ensembles that we could compare to in the system. So we start out with this system, exactly 1 atom per lattice site. This is an eigenstate of our Hamiltonian for strong interactions. So we start with 1 state here. Oops, sorry. I'll go back here. So we start out over here with a eigenstate here. Then we jump to a lower lattice depth. Now this Hamiltonian has new eigenstates, and if we decompose this eigenstate into the new eigenstate basis, we actually see, well, this is actually going to be a superposition of many of the eigenstates of the new Hamiltonian we're quenching to, which of course gives rise to this time evolution of the many-body system now. This is where all the time evolution comes from. And now we can compare to, let's say, we can have the same average energy in the system. This is fixed, of course, by our initial state. And now we can compare the, let's say, probabilities that we measure for these occupations, for example, for this local system of one side or this three-side system, for different temperatures in the system, and for different ensembles that we can assume for a thermal system. So we remember you have the microcanonical ensemble, you have the canonical ensemble, or you can have just an eigenstate, single eigenstate. And for all those systems, we can come up with predictions from statistical physics what the probability occupation number on a given lattice site would be. And these are drawn out here in these different colors, comparing the different ensembles that we can have, diagonal, microcanonical, canonical, eigenstate, compared to the measurement. And you can see actually for both system sizes, 1 or 3 sites, this agreement looks actually strikingly good. Yeah, so all those ensembles, those thermal ensembles agree what the measurement shows us what the system looks like locally after this quantum state evolution, even though the global state is pure. That's the key feature, right? So there's one final thing that's interesting here, that you can see that the grand canonical ensemble, this one here, the grand canonical ensemble, for larger system sizes, here, this is the 3-side subsystem size, agrees less well with the experiment than the other ensembles. And this just shows us that the reservoir, this 3-side, system here, which acts as a reservoir, this is not really large enough to act as a good thermal reservoir for our equally sized system over here. So the reason why the statistical physics works is because usually the remainder of the system is huge compared to the subsystem you're looking at. But when the subsystem is of equal size compared to the, let's say, remaining reservoir of the system, you don't expect this to act as well as an ensemble, thermal ensemble. And this is indeed what you actually also see in the experiment. And this is where this deviation in the 3-side subsystem is larger than in the 1-side subsystem case, where actually even the grand canonical ensemble actually works strikingly well. Okay, that's what I wanted to tell you about thermalization, how you can measure thermalization in these quantum many-body systems, and really beautiful experiment from Mark's experiments showing you how you can probe these entanglement entropies with this really neat trick of this many-body interference homomundle experiment. All right, in the final part, I thought we'd just do something fun, an older experiment, but something that should be a little bit easier to understand, but I think fun and also nice in the context of thermalization, and that is a topic of negative absolute temperatures. So I just remind you again, we're back to the realm of statistical physics. We believe that systems thermalize and statistical physics hold, thermodynamics hold. And I remind you again how we define absolute temperature in statistical physics. It's namely the derivative of entropy versus energy gives us 1 over the temperature. Okay. Now, usually when you add energy to the system, you add entropy to the system. So this slope is positive. And so entropy increases with energy. That's the usual situation we face. But there can also be a situation where, in principle, this is negative, where actually when we add energy to the system, actually, for example, energy decreases. And that's perfectly fine. There's nothing wrong with such a situation. Thermodynamics applies equally well to a situation where this derivative is positive or negative, to a regime of positive or negative absolute temperatures. Okay, so let's look at the requirements for this negative temperature to work out in the experiments. So typically when we talk about canonical ensembles, we think of a thermal system having this probability distribution where we have the eigenstates occupied by these Boltzmann factors with this exponentially decaying probability of having the ith state actually populated in the system. Okay, and for that to work, for this to be normalizable, you actually have to have a minimum energy state, a lowest energy state in the system. Otherwise, this would just diverge. So you have to have a minimum energy state here so that you can normalize this probability distribution. So for positive temperatures, we actually need to have a lower energy bound in the system. Let's just try the do a simple thing. Let's just say, okay, let's imagine we have negative temperatures. So we go from T to minus T. So now we have an exponentially increasing probability distribution. And again, for this thing to be normalizable, to make sense to us in terms of a probability distribution, that will then require an upper bound in energy for this to work. So this will work in systems which show an absolute upper bound in energy that we need here. This has been known since the 50s that such systems exist. And maybe the simplest systems that, for example, I described in this beautiful paper from Norman Ramsey are spin systems. You know, it's very easy to see that those systems have a lower bound in energy and an upper bound in energy. For example, if you take a spin Hamiltonian and you have all the spins pointing up, for example, you have in a B field, then you have a minimum energy. And if the spins point all in the opposite direction, then you have a highest energy state in the system. So it's quite natural for these spin systems to have both a minimum energy state and a maximum energy state. And that's why those systems actually support both thermodynamic states at positive and negative absolute temperature. And this has been shown here in this beautiful experiment by Purcell and Pound in the 50s. Also for antiferromagnetic systems, later also actually a cold atom experiment in Wolfgang's group, looking at how you can realize these negative absolute temperatures in the ultra-cold atom systems. So what I want to discuss with you now, how you can realize something like that for a gas, for a moving system. So where you have a gas of atoms, how can that be at negative temperature? What does it mean for such a system to be at negative temperature? So not for fixed spins, but really for motional particles, for your rubidium atoms flying around in, for example, in our optical lattices. So let's look at our Bose-Hubbard model, which now is our guinea pig model for lattice models. And we have three terms that are relevant. We have the kinetic energy term, describing the hopping of the particles. We have the interaction energy term, describing the interactions of the atoms on my lattice. And then typically in experiments we swept under the rug, we also have this harmonic trapping potential, which is also present there. And now to say whether a system supports positive or negative temperatures, we have to look at the bounds of those individual terms in the Hamiltonian. So let's look at kinetic energy. Well, if I'm in the lowest energy band of my system, kinetic energy is bounded from below and from above, because I have an energy band. It has a lower energy point and an upper energy point. So that's fine. That's great. It supports positive and negative temperatures, kinetic energy. Interaction energy for repulsive interactions is a little bit critical because there's a lowest energy state where you have no interaction energy, which would correspond to just individual atoms on different lattice sites. There's never double occupancy, so there's no interaction energy. So that interaction energy is zero. But when you start piling the atoms on top of each other, you can increase the interaction energy. And in principle, that's unbounded because you can just add more and more particles, add them more and more on top of each other. So that's unbounded. Potential energy of our harmonic trap is also unbounded. So that has a lower energy point here at this minimum of the harmonic potential, but no upper bound in energy. Now, in order to have a situation, so this is a situation where you can have a positive absolute temperature. You have a lower bound in energy, but you don't have an upper bound in energy. For the situation here, now we can actually realize something when we change interaction energy to attractive interactions. We go from repulsive to attractive interactions, and we go from a trapping potential to an anti-trapping potential. Then actually we can reverse here the bounds for interaction and potential energy. So for now, for attractive interactions, it's bounded from above, but not from below. Potential energy for this inverted harmonic oscillator is bounded from above, but not from below. So this is a situation where we can actually have negative absolute temperatures in the system. So let's just look at kinetic energy to understand what it means to have positive and negative absolute temperatures. And let's look at the entropy of our system here, entropy, as a function of energy that we have in the system. Now, if I'm in the lowest energy state of my system, which would be in terms of kinetic energy, all the atoms in the Q equals 0 state of my Bloch band, then I have zero entropy because I have a pure state. All the atoms are in the same quantum state. There's zero entropy in the system. Likewise, if I put all my atoms in the maximally excited state, it's also a pure state. There's also zero entropy. And then I can distribute them, for example, here equally over all of the states in my energy band. And then I have a maximum possible entropy, which is just happening precisely at the middle of this energy limits here, Min and Emax, that I have, where I have a maximum entropy case. So the entropy as a function of energy is this dome-shaped feature in this bounded situation of kinetic energy. Now we can just plug in our formula for the temperature. Remember that was equal to ds over dE, and plot the temperature. And we see in this region where the slope is positive, we have positive temperature. And in this region where the slope is negative, we have negative absolute temperature. And actually this goes from 0 positive temperature to plus infinity positive temperature, jumps to minus infinity, and then goes back to -0 absolute temperature. You might wonder, well, is this divergence something I have to worry about? Well, I would rather say it's just an artifact of history, because really, if you look at beta, if we would have defined beta, then it would just be a continuous variable going from minus infinity to infinity, 1 over kBt. All right, okay, but how do we get there? How do we do this in the experiment now with the interactions and the trap? So here's the trick that we can do in the experiment. So we start with the superfluid in the Q equals 0 state. We ramp up our lattices and turn this into a mod insulator that Wasim has told you about. So now you are in the very strongly interacting repulsive limit of your system with equal occupations of the different Q states, 1 atom per lattice site in the system. And now we do a rapid switch. Now I use my Feshbach resonance to rapidly switch U to -U. And the trapping potential, I switch from a trapping potential to an anti-trapping potential. So I switch a harmonic trap like this to a harmonic trap like this. And so U goes to -U, V goes to -V. The state is the same. I do this so fast that everything is basically non-adiabatic. And then I ramp down my lattice potential again. And then actually what should happen is that now the conditions, we are in the highest energy state of the system. And in this highest energy state of the system, we should be actually condensing now to these points where we are at the boundaries of the Briand zone, not anymore in Q equals 0. At this upper band gap point, the system is now and basically is a negative temperature state at the upper band edge of the system. So here's how this looks in the experiment, how we can check this. You remember you can probe whether you're in the superfluid or mid-insulator regime by looking at the interference patterns in the system. So here's the superfluid regime where you have nice interference pattern. You ramp to the mod insulator regime, the interference pattern vanishes. If you just ramp back down again, you can recreate the interference pattern again. You see you get a state at positive temperature again. And this interference pattern tells you that you're actually in the Q equals 0 state. But if you do the same experiment, and now you do this switching, you go from U to -U and to V to -V, and you ramp back down the lattices, you see you also condense again, but you see that the interference pattern you get now is the one that you expect if you condense at the upper band edge of your system at this maximum energy state at the absolute negative temperature. You might wonder, there's been these beautiful experiments actually in Boulder on the attractive interactions. When you take a BEC and you turn it to attractive interactions, this thing is actually unstable, it collapses. You might ask, is this system unstable now because I've tuned to attractive interactions? Turns out no, actually it turns out if we look at the, for example, visibility of this interference pattern as a function of hold time in the lattice, we see that the positive temperature state, the blue curve here, is as long-lived as the negative temperature state with attractive interactions. So the system is absolutely stable at this negative absolute temperature, even with negative interactions in the system. We can actually determine the temperature by just fitting a momentum distribution to our interference pattern, and you just take your standard distribution function of your momentum distribution for, finite temperature state, your basically Bose-Einstein distribution, and from that you can now see that for this positive temperature state, we have the blue curve, and for the negative temperature state, we have the red curve here showing us the inverted population of those states, of the different momentum states, and we can derive the temperature from that, and it turns out to be minus 2.2 tunneling energies divided by kBt is the absolute negative temperature that we realize in the system. So to finish off, I just want to comment on a few things maybe you can discuss or think about, and we can resolve them in the last lecture tomorrow, some things that are really peculiar, and then I will actually I finish just 2 more slides. So one thing that's interesting with when we think about stability of matter, we require that the increase or ds, the slope of ds divided by dv, is always larger than 0. So if we basically otherwise the system would collapse onto itself. Okay, this ds dv is nothing than absolute pressure divided by absolute temperature from the first law of thermodynamics. And if absolute temperature is negative, but our system is stable, this requires actually that absolute pressure is also negative. So not only is absolute temperature negative in the system, but absolute pressure also. And that's interesting because it actually means that you have a system now where usually when you have a system with positive absolute pressure, you have to perform work to compress it. Here you have a system where you have to perform work to actually expand it. Also, if we plug in just Carnot formula, you can actually see, you can realize Carnot engines with larger than unit efficiency. If T2 over T1 is negative, if we run a Carnot engine between a positive and negative temperature reservoir, this would be positive and give us an efficiency larger than 1. Don't worry, there's no perpetuum mobile here. Otherwise, you could stop my lecture, you would not believe me anything, but maybe you can think about it, why that is. And the final thing I just want to say, also, if you send an impurity through such a gas with negative temperature, actually, instead of slowing down, it would actually accelerate. Yeah? Why is that? Well, think about first the positive temperature case. If we have a gas or fluid at positive temperature, we send an impurity through that. That impurity will basically increase the entropy of the system, will increase the disorder in the surrounding environment. In order to increase the disorder, you have to increase the energy of the surrounding environment. And that energy comes from the impurity, and that means the impurity will slow down, so there's friction. The opposite is true for the negative temperature state. So for the negative temperature state, you also, when you shoot an impurity through the negative temperature gas, it will increase the entropy. But increasing the entropy for a negative temperature gas means actually decreasing its energy. Well, where does that energy go? Well, it actually goes to the particle. That means that particle will accelerate. So instead of slowing down, the particle that you shoot through a negative temperature gas will actually accelerate. Okay. So again, something for you to think about. And maybe I have time, I can discuss tomorrow these final thoughts of why people like or dislike negative absolute temperatures. But yeah, I think that's a good point to stop here and keep these questions open for our maybe final class tomorrow, where we can resolve these puzzles. Yeah, what's going on? All right, thanks a lot.
Thank you, Immanuel. Are there any questions? Since we were a little short on the questions today, I think now is your chance to probe weird issues like negative temperature.
Could you tell us why the system is still stable? You mentioned that with attractive, it should have been unstable, the BC, but it turns out it's stable.
Well, it basically comes from this absolute pressure. That absolute pressure in this system is also negative. That really actually, in order to, when you want to expand this system, and you can think about it microscopically, I want to leave to you to think about that. It's actually interesting to think about why, when you expand such a system, would you actually have to perform work when expanding the system? Okay, so that's what happens here. This is where absolute pressure also becomes negative in this system, where the total term is basically, so the total sum is basically positive again. There's another peculiar thing you might be worried about is why, if I, let me go back here in my slide actually, why, if you always, when as an experimentalist, you should always be worried when we work with these anti-trapping potentials. So if the trap is inverted parabola, why don't those particles just fall out of my trap? Why don't they roll down the hill?
I guess it's the same. You have to do work to expand.
No, yes, here's a different argument. What can you say about kinetic energy when you roll down the hill? What happens to kinetic energy? If you just take an inverted parabola, you just put a marble on top and you see it roll down. What can you say about kinetic energy?
I guess that should increase, but here it's already.
Should increase more and more and more, right? You're converting potential energy to kinetic energy. But here you have bounded kinetic energy. You cannot increase the kinetic energy above a certain level because you have an upper bound for the kinetic energy here. And you are already in the state with maximum kinetic energy. You're already in the upper state of the band, which is the maximum kinetic energy. It means you cannot roll down simply because you're an isolated system. You cannot convert any more potential energy into kinetic energy. But this only works, of course, in an isolated system. If you have something else you couple to, then of course you have other degrees of freedom. You can convert the energy, but here you cannot convert potential to kinetic energy. So it's absolutely stable in this inverted parabola.
But you also have higher bands, right? Can you couple to them?
Those are a problem. Yes, we absolutely neglect them. You're not allowed to couple to higher bands. So the system has to stay in the subspace of this lower band. Absolutely right.
So I have a question, Immanuel, if no one else is going to jump in. So another way to say what you've done here, you did say it, I'll just say it again, is that you've made every term in your Hamiltonian negative. And it was, so if I forget about thermodynamics, because that's all confusing, I think only about time evolution, that's like time running backwards. So it makes me wonder then, if you can do a really generalized spin echo experiment with this kind of setup.
Yeah, we could.
Body spin echo.
Yeah, I have to disappoint you. There's one term we didn't really change, but it's the one where we have about two bounds, and that's the kinetic energy. It didn't change the kinetic energy. When we switch from U to minus U and from V to...
Okay, fine. So there's one more term you have to do. You have to add a Peierls phase of pi.
Exactly. You would have to go from a non-thermostatic system to your Floquet system that you know, where you invert the band. And if you can do that, then you can invert truly all three terms and you can do a full echo, as you say, full many-body reversal, time reversal of your system. Absolutely. But that's tricky, as you know. That has the Floquet systems have other nasty problems.
Yeah, yeah. I wonder if you
could you do something dynamically where could you just give all the particles as part of your echo a pi momentum kick?
Yeah, but here we're starting out with them all being localized, so we have the entire band populated. That's also what we need here for this trick to work, to go from the lowest energy state to the highest energy state. So we're basically, so the state here, this psi that we have here is the same psi as over here, but we're going now, this psi is the minimum energy state in the Hamiltonian with the repulsive interactions and a trapping potential, but it's the maximum energy state for the inverted Hamiltonian when we tune U to minus U and V to minus V.
Sure, but I'm thinking for Ian's suggestion to look at some sort of, reversal of the dynamics. When I do the reversal of the U and V terms, couldn't I do a pi kick at the same time at the momenta, and then it would be like flipping the tunnel?
Yeah, I guess, Caden, if you would just do it for a condensate, that could work. I think that's right. Where you just go from Q then to the edge of the boson, where you expect same dynamics. But if you, of course, you have more states populated in Q space for strongly interacting systems, that wouldn't work anymore, right?
Maybe you can invert the band.
Yeah, that's what Ian is suggesting. That's what Ian is suggesting. And the way to do it, you should know by now also, is to shake your lattice. If you shake the lattice, if you do this Floquet modulation, then you can actually reverse the coupling. J, you remember your Bessel functions in the J, you can turn J to minus J. That's precisely what you need. But we didn't do that in this experiment. It wasn't needed here.
All right, so I think since Thierry talks kind of soon, it's a good time to break. And tomorrow, Immanuel will give us last lecture. So if there's any pressing questions now, you can interject the beginning of his lecture to sort of link them together.
Sounds good. Bye, everybody.
All right. See you everyone shortly.